So in this video, let us try to understand the process of getting the viscosity of a given liquid with the help of Stoke's method. Previous to this video, the video was to determine the viscosity of water with the help of Poiseuille's method. Now any other thicker liquid, the viscosity of which cannot be determined or determination is difficult with the help of Poiseuille's, that can be determined with the help of Stoke's method. So let us see the Stoke's method. Let us see the instrument. In the instrument, this is a heavy base. On this heavy base, there is a glass tube. This is a glass tube having a diameter of approximately 15 to 20 centimeter and having the complete length of say 1 meter. You can see this. This is the glass jar. This is a glass container and having 20-25 centimeter diameter, and the length is approximately 1 meter. Now this is supported by the stand. These three rods are for the support of this. Then above this there is a funnel. This is a funnel, and funnel is used so that we can put the balls exactly at the center or the axis of this glass tube. You can see the three markings on this with the help of rubber band. This is the first marking. You can see this is the second marking, and you can see the third marking here at the bottom. So this is the marking, this first marking. It is from the top of the liquid. The distance of this first marking from the top of the liquid is kept approximately 15 centimeter, 10 to 15 centimeter. Then this is always kept constant, it is not changed. The second marking and the third marking, this one, these two can be adjusted with respect to the first one, with respect to this first one. With respect to this first one, if I keep the distance of the first marking say at 30 centimeter, then between second and third I again keep the distance equal to 30 centimeter. So two equal distances are kept whenever the marking are to be adjusted. The first, that is the top marking, it is once fixed, it is not changed. This acts as the reference. With reference to this, we adjust the position of the second and the third mark, and approximately the distance between the first and the second is exactly equal to the second and the third. So this is all about the instrument. Except this, there is another instrument, and that instrument is the stopwatch. So let us try to see the stopwatch. This is the stopwatch. You can see this is the on off switch. Here it is on off switch. Whenever I put in the on position, this gets on. You can see there is the measurement of the hour, minutes, seconds and fraction of seconds. So obviously I can get 1/100th of the seconds reading also with the help of this. This three switches are there. First is the stop and start switch. Second is the adjustment switch, and third is the setting switch. So we do not use this setting switch because this is not in our preview of using. We are going to use only the stop, start and the adjustment. When we push it once, the stop clock starts. Second time I push, it is switched off, means the time counting stops. Then when I push this adjustment, again it is adjusted to 0. So this is the second instrument which we are going to use. Except this, there is a third instrument, and the third instrument which we are going to use is this screw gauge, and we are going to deal with the screw gauge in details when we are going to measure the radius of the ball. So I am not discussing it here. You know it is screw gauge. So we will be using it, and while using I will be explaining each and everything to you. Okay, now let us start how to experiment. Now let us see, the first part of the experiment is to determine the radius of the balls, steel balls which we are using, and to measure the radius of the ball the instrument used is this screw gauge. Now to understand the screw gauge, let us see what are the parts of this. This one is the rotator. Whenever we want to open this screw gauge, we use this. This is lock. When I push it in this direction, you cannot move this head scale. When you unlock it in this direction, now this can be moved, this can be rotated. So you are seeing the scale here. This scale is the head scale or the circular scale. And the scale which is now visible, this is the main scale. This is main scale, and this is the circular scale or the head scale. Now you can see this is the main scale and this is the head scale or the circular scale. This is the main scale marking, 0 mark means this is the reference of the main scale, and here you can see for this horizontal line is used as the reference to read this scale. So whenever we open it from here, and whenever we want to close it, we do not use this portion, we use this, and we are going to rotate it until we get a click sound. For example, I am showing it to you. I am rotating it with the help of this. See, you can listen this sound. Okay, when this sound comes, we stop rotating. Now the first thing is, I have to determine the zero error first. So to determine zero error, we see where is the 0 mark of the head scale and the 0 mark of the main scale. You can see this is the main scale 0, but when I have tightened it, I have brought it in a position where the click sound is there. The 0 of the head scale has crossed the reference line, and the number of division crossed is 1, although it is not 1 exactly, but yes, now you can see it is 1 division has been crossed. So there is an error, and the error is of 1 division, and that is a negative error because it has overshoot the mark. Because it has overshoot, so it is negative error. If it would have been here, somewhere here, we could have told that this is a positive error, but because this has crossed, and that's why 1 division's error is there, 1 division's negative error is there. Now the next thing which we have to understand, we have to see is, we have to find the least count of this screw gauge. For getting the value of least count, what we do, we give rotation to this head scale, and that rotation is even number of rotations, means either we are going to give 2 rotations, or we are going to give 4 rotations or 6 rotations. And after giving this much of rotation, we are going to see how much distance have been traveled in the head scale, main scale. So let me give the rotation. From 0 I start, I 30, 40, 45, again I reach 0. So 1 rotation, second rotation, third rotation, and see I have given 4 rotations. And in 4 rotation, you can see that 2 divisions have been crossed. 2 division means 2 mm distance has been traveled. So in 4 rotations, we get 2 mm's distance traveled. So pitch of the screw becomes the distance traveled, that is 2 mm, divided by the number of rotation, that is 4. that is 2 by 4 is equal to 1 by 2, it is equal to 0.5 mm. So pitch of the screw becomes equal to 0.5 mm or 0.05 centimeters. Now, to get the least count, the formula of least count is the pitch divided by number of total divisions on the head scale. So, number of total division you can see 45 plus 5, that is equal to 50. Total 50 divisions are there in the head scale. So, pitch, that is 0.05 centimeter divided by 50 is equal to 1 divided by 1000, which is equal to 0.001 centimeter. That becomes the least count of the instrument. So, I have shown you how to get the zero error, which is 1 division of head scale in this specific case. I told you how to calculate the pitch. Pitch is number of total distance traveled divided by number of rotations, that gives the pitch. This pitch, when divided by the total number of divisions on the head scale, that is 50, total 50 divisions, so that gives us the value of the least count. So we have calculated least count. Now, when we want to find the diameter of a ball, then what we are going to do, let us see. So I am going to take the radius or the diameter of the ball. So I am having two sized ball. One ball is this and second is this ball. So I put it between the gap of this spindle. One is moving and second is fixed. So I put it like this. See, this way I slide it between these two jaws. Now I tight with the help of this screw. Okay. So the click sound is there. Now I am not going to rotate. This is the position where I have to take the reading. Now, to take the reading, I have to take the main scale and the circular scale reading. So you can see the scale here. If you want, I can show it with the help of this magnifier. Is it visible? No. So we are seeing what is happening. The total distance traveled in the head scale is to be determined. So it is 1 mm, 2 mm, 3 mm plus 0.5, that is 3.5 mm. This is 0 mark, this is 0.5, 1 mm, 1.5 mm, 2 mm, 2.5 mm, 3 mm, 3.5 mm. So main scale reading is 3.5 mm because 3.5 mark has been crossed. So 3.5 mm becomes the reading of the main scale. Now we want to see what is the reading in the circular scale, and in circular scale you can see the reading is 0 because this 0 is coincident with the reference line. So 0 is the reading of the circular scale or head scale and 3.5 is the reading of the main scale. So in this way I can get the readings for getting the diameter. When I want to change, I want to take the diameter of the second. Obviously I again lose it, let the ball drop and I put the next ball here in the same way as I put the first one. See, now I tighten it with the help of this screw. The click sound is there. Now I have to take this reading, I lock it. Now I get the reading. Now you see the reading here in this specific case. For the second, the main scale distance traveled is 1 mm, 2 mm, 3 mm, 4 mm and 4.5 mm. 4.5 mm distance has been traveled in the main scale. So main scale reading becomes equal to 4.5 mm and the circular scale reading is, you can see it is 25th has been crossed, 26th has been crossed, 27th has been crossed, but 28 is not crossed. So 27 is the head scale reading. So main scale reading is 4.5 and the head scale reading is 27. So in this way we take the reading. Now to get the total reading, this 27 is multiplied by the least count, that is 0.001, and added with 4.5. So it becomes 4.527 mm, or it is equal to 0.4257 mm. Okay? So 4.5 plus 27 multiplied by 0.001. Okay? So that will be the reading of the diameter. Sorry, while taking the reading of the head scale we made a mistake. This one is 20 mark, so the division crossed is 21, 22. So 22nd division has been crossed, 23rd division has not been crossed. So the head scale reading or the circular scale reading will be equal to 22, not 27, it will be 22. Sorry. Second thing, to get the velocity of the ball inside liquid, we adjust the distance between the threads or the marks. So I keep the scale here, taking this first mark as the reference. I set the distance between first and the second to be equal to 35 centimeter. This is the 35 centimeter mark. So I have adjusted 35. Similarly, between the second and third mark, again I have to set the same distance. So I am keeping the scale as the reference to the second, and I am measuring the position of the third, which is again 35 centimeter. So both the distances are now 35, set for the experiment. Now we keep the balls dipped inside the liquid, the viscosity of the liquid which is to be determined. The same liquid which is inside this tube, the same liquid is here, and the balls are dipped inside that liquid. So that when I put these balls inside the liquid, there should not be any air layer between the liquid and the ball. Ball is going to fall in the liquid itself, and that's why it is dipped inside the liquid. Now we pick one of the ball from this container and we take it with the help of this fork, and now we put it inside the glass tube. So this way I put the ball inside this liquid. You can see it is moving inside the tube. Now we are going to take the readings. So see what I do. I am keeping ready my stopwatch and I am holding it very near to see this mark, first mark. When the ball is going to cross the first mark, I am going to switch on, and when it is going to cross the second mark, I am going to switch off the stopwatch. So let us start the experiment. You can see the reading. The reading is 1 second 0.58 second, means 1.58 seconds. So the distance was 35 centimeter and the time taken by the ball to cross the distance between first mark and the second mark is 1.58 seconds. Now we want to take the same ball and we are going to measure the time taken by the ball to cross the distance between second mark and the third, that is the lowest mark. So again I use the same ball, I drop it inside the liquid and I start and stop the stopwatch. Now you can see the reading is 1.78 second. The distance traveled is 35 centimeter and the time taken is 1.78 second. So that is the two readings I have taken. Now using various balls, we have to repeat the same experiment. First we have to take the distance that is between the first mark and the second mark. In the second step we have to take the distance between the second mark and the third mark, and the distance between both these two are always kept constant, means for the first reading I have taken 35 centimeter. In the second reading, I can take 30 centimeter. For the third set of reading, I can take 25. For the fourth, I can take 20 centimeter. By changing the distance, I go on putting the ball inside the tube and find the time taken by the ball to cross a specific distance inside liquid. That much is the experiment. If you do it properly, you are going to get proper value of the viscosity of the liquid. So that's all in the experiment. Let us try to find the value of, the readings. Let us try to see the readings and then calculate the viscosity of the liquid. So let us see the reading. This is first table and it is for the measurement of terminal velocity of a given steel ball. So ball number A, and we have taken two distances, distance between first and second mark and second and third mark. The distance has been kept equal, that is 40 centimeter. So mean distance becomes equal to 40 centimeter. For the first, we have taken time which was equal to 1.8 seconds. For the second, it is 1.90 second. So the average of these two becomes 1.85 second. Now, this is the mean distance traveled, this is the mean time interval. So distance, that is s, divided by t gives us the velocity, and the velocity becomes equal to 21.62 centimeters per second. Then in the second set, we have reduced the distance to 35 centimeter between both the separations, first and second, second and third. So the mean distance becomes 35 centimeter. Time taken is 1.53 second for the first distance of 35, 1.72 for the second distance of 35. The average is 1.625. So the average distance 35 divided by average time interval 1.625 gives us the velocity to 21.54. Similarly, for 30 centimeter, same ball, we have taken the velocity. Then for another ball, bigger ball, we have taken the 30 centimeter separation, and the time was 1.09 and 1.18, so the average is 1.135, and the velocity of the fourth ball we used is 26.43. It is not equal to the velocity for the other ball. You can see for other ball, for every ball it is 21 point something, but it is 26. Velocity has increased because this is a bigger ball, that's why the velocity is large. For the bigger ball, 35 centimeter, the velocity comes to be 26.62. See, for the bigger ball, again the velocity is approximately same, that is 26 point something. So in this way, we can get the terminal velocity for the different balls. So the second observation is the measurement of the radius of the ball. For measurement, first we have determined the pitch. So we have calculated the number of rotation was given equal to 4. The distance traveled in the main scale was 0.2 centimeter, 2 mm or 0.2 centimeter. So the pitch of the screw, that is equal to d divided by n, is equal to 0.2 divided by 4, which is equal to 0.05 centimeter. This is the pitch of the screw. Now the least count is pitch of the screw divided by total number of division on the head scale, that is circular scale. So pitch is 0.05 divided by 50, which becomes equal to 1 divided by 1000 centimeter, that is 0.001 centimeter is the least count. Now the zero error, that is number of divisions in the head scale multiplied by least count. Here in this case, in this specific case, 10 divisions had been crossed, 10 division overshoot was there. So 0.001 multiplied by 10 becomes equal to 0.01 centimeter. This is the zero error. Now the A ball's main scale reading was 0.35. Circular scale reading was equal to 37 division multiplied by 0.001 becomes equal to 0.037. Now 0.35 plus 0.037 becomes equal to 0.387. So this is the observed reading. Now whenever we want to get the corrected reading, the error is subtracted with sign. Zero error here is negative error. So this negative error is subtracted from 0.386 with sign. So basically when my negative error is again subtracted, it actually adds up. So adding it, it becomes corrected diameter becomes 397. So this 397 divided by 2 to give the radius of the ball, that is equal to 0.199 centimeter is the radius. 0.199 is radius. So we get the volume of the ball. Volume of the ball is 0.0327. We have used the formula 4 pi r cube divided by 3. So it is 4 pi r into r divided by 3. So the volume becomes equal to 0.0327 cc cubic centimeter. Mass of the ball is measured or it is provided in the experiment. So mass is equal to 0.26 grams. So this 0.26 grams divided by volume gives the density of the ball, and the density of the ball is 7.94. For the first ball, we have calculated everything. We have calculated the corrected diameter, corrected radius, volume, mass and density. So density will be required in the formula. For the second ball, again the same ball was used, so the reading is approximately same. You can see the ball D. For ball D, the main scale reading was 0.45. Circular scale reading was equal to 14 division multiplied by 0.001 gives us 14 multiplied by 0.001 is equal to 0.014. Added it with 0.45 gives us 0.464. Then the zero correction is taken, 0.01 is added to this to give 0.474, that is corrected diameter, divided by 2 we get the corrected radius. The 4 pi r cube divided by 3 formula gives us the volume. Mass, measured mass of the ball is 0.438. This mass divided by volume gives us the density, which is equal to 7.86. And next thing which is provided in the experiment is the density of the given liquid, that is glycerol, that is equal to 1.77 gram per cc. The density of the ball is calculated here. The density of the liquid is already provided here. Now let us see the calculation. Now let us see the calculation. The formula for calculation is eta is equal to 2 by 9 r square sigma minus rho multiplied by g multiplied by t divided by s, and actually s divided by t is equal to v. So I can rewrite the formula as 2 upon 9 r square sigma minus rho g divided by vt, where vt is the terminal velocity for that specific ball, r is the radius of the ball, sigma is the density of the ball, rho is the density of the liquid, g is the acceleration due to gravity, and v or vt is the terminal velocity. So let us put the value for ball A. For ball A we have taken reading of radius, density and terminal velocity. So we put the value here. So we show it as eta 1, the viscosity for first ball, that is ball number A. It is equal to 2 by 9 multiplied by the diameter of, radius of the ball square, that is 0.199 square, multiplied by sigma, that is 7.94, minus rho, which is equal to 1.77, multiplied by g, that is 980 centimeter per second, divided by the velocity, that is 21.62 centimeter per second. When I calculate it, the value comes to be equal to 2.46. Now similarly, when I calculate the same for the second ball B, the value of eta 2 becomes equal to 2.6. When I calculate it for the third ball, that is ball number 3, the eta 3 becomes equal to 2.46. For the fourth ball, that was a bigger ball, I calculate the viscosity and it comes to be equal to 2.81. Now for the fifth ball, it comes to be equal to 2.79. Okay. Now we have got the viscosity using different 5 balls. Now I want to find the mean value of the viscosity. For that I get the mean, that is eta, which is equal to eta 1, eta 2, eta 3, eta 4, eta 5 divided by 5. Putting the value 2.46, 2.46, 2.46 plus 2.81 plus 2.79 divided by 5, it comes to be equal to 2.596, or rounded off it becomes equal to 2.60 poise. So that is the viscosity of the liquid we used, and here the liquid used is glycerin, and the viscosity of the glycerin is not equal to 2.59 poise. Instead, the pure glycerin is having the viscosity of say 6 poise, but because this glycerin is having the property of hygroscopy, so it absorbs the humidity, and absorbing humidity its viscosity decreases. So the glycerin here being used has absorbed certain amount of humidity, and that's why the viscosity comes to be less than the viscosity of the glycerin. So that's all in this experiment. I think that you have understood the experiment as well as the calculation, and you are ready to perform it with full accuracy.